Okay, next problem in the lead code we are solving is minimum path sum. Okay, so basically here we have got the grid, m cross n grid. We need to traverse from top left to the bottom right, and we need to return the what is the minimum path that we can go. These are the weights. Okay, like these are the weights, and we need to take a sum of it, like different paths, and we need to return the minimum paths. Okay, now let's see that how we can approach this problem. So basically what is then asked here is we'll be starting from here and we need to go here. Okay, so whenever we traverse, let's say that I can go from any n, there are n number of ways that I can traverse, right? This is one path, or maybe this path, or I can go from top to this path, or there can be n number of ways, correct? So what's happening here is, so basically these are n number of ways. We need to find a sum for each. We need to find a sum for each, and then whatever the, like, I mean, out of the total sums, right, we need to return the minimum of it. So whichever the efficient way, right, that will be the efficient one. Actually, whichever is the minimum is called as an efficient one here. Okay, and it can be solved via backtracking, correct? So I can just write an algorithm for a backtracking, saying that go left, go right, and once you go right, you go left to try the combination for. And also one condition I missed to tell is, like, how to traverse here is there is only two way that you can traverse. Let's say that you are in some box, you can either go to the bottom or you can go to the right. Okay, so now that we know that how we know that how to traverse, so using the backtracking we can write an algorithm so such that telling, like, let me say, if I am here, right? Okay, if I am here, I will write an algorithm to try to the right and to the bottom and to the right. So once I am here, try to the bottom and try to the right. Right, once I am here, try to the right and try to the bottom. We need to handle the overflow because there is nothing here. So once I am here, try to the right and try to the bottom. Okay, so when we traverse and we reach the end here, correct? So by this time we must have also be tracking the sum for each of the, taking sum for each of the path that we are traversing, right? So we can solve it. Okay, so but as you can see here, right, like there will be n number of duplicate operations that we are doing currently. If I say it right, let me clear it, it's getting dirty. Okay, as we just discussed about the backtracking, right? We can solve it. We'll get an answer. But what you can see here is, like, just by simple, like, I mean, this is a 3x3 grid, right? Here only you can see that there are multiple duplicate tasks that we are doing here also, and we are coming from this, and right, there are multiple. We are doing the same calculation and again. This will add the much time complexity, right? So, like here, there are duplicate things that are happening, right? If we are able to somehow reduce this duplicate operations, it means that we can solve it efficiently, correct? Why to solve the same operation and again, right? So that's why, to improve the backtracking algorithm, like, I mean, or the any recursion problems, right, what we so one drawback usually that will be that will happen whenever we are solving backtracking is, like, we'll be doing the same operation again and again. So how are we going to solve it? Using a dynamic programming. Like, what is dynamic programming? If we store whatever the operation that we are trying to do here, right, if we are able to store it somehow and reuse it for a better use case, like if you reuse it, it's called a dynamic programming here, right? So let's see that how we can actually use that principle here. So let me just clear it out. So let's say that, okay, so we just saw that there are n number of ways, right? So let's say that before actually coming to this, right, let's say that I can go to this 5 from here or from here, right? So, like, I can, there can be different ways, right? I can go here, I can go from here, and like, I mean, so whenever I go to 5, I'll be doing the same computations, correct? I will be doing this, I will be doing this, and I'll be doing, whenever I, let's say that if I come in this path also, right, I need to do the computation for this and this, right? So it's a duplicate thing here. So what we instead can do is, I will calculate the path sum for 5 initially. Okay, so what will be the path sum here? If I can go to end like this or like this, okay, what will be the path sum here? It will be 7, it will be 8 here, right? 5 plus 2, 7 plus 1 is equal to 8. 8 plus 1, okay, so 7 plus 1 is 8. Okay, so which is minimum here? Which is the efficient path? This is the efficient path, right? Like, I mean, so what we can simply do is, I'll rule out the 5 and just save the 7 here. Okay, save the 7 here. So what does it mean is, so now if anyone comes from this, either this path or this path, I won't be doing the same calculation and again here, right? I've already saved it as 7, so this value can read that value and updates its path sum. So so far it traversed the value as 2, right? 1 plus 1 is 2. It can read this value and it can do it like 2 plus 7 is 9, right? This is the path sum for this traversal. Okay, like whatever, if I start from here, this will be the traversal 2 plus 7. So if this guy comes, so 1 plus 4, so far it traversed 1 plus 3, which is 4, and you will just read the value that is present here. So 4 plus 7, it will be 11. So we will consider this as the one another path sum. Okay, so now what is happening here? So basically we can just store some values and reuse it, correct? So we here we explicitly saved the 5, correct? So this helped the saving us doing the same calculation again and again here, right? Again, let's say that initially we used to solve for 5 twice, but now we are doing it only once, right? So what does it mean is, if you like, I mean, whatever the greater element, right? These are the initial elements, I can say these are the end elements. So if we store the values for the end elements, I can use it for the initial elements. This will reduce the number of operations that we are trying to solve. Okay, initially here for we took an example for 5. Instead, we can also save it for 2 also, right? We can save it for 1 also, we can save it for 1 also, here also, this also, right? We can save it for this also, like whenever we try to save, the previous element will take a benefit out of it. Okay, so now let's just see like how it looks once again. Okay, to simplify, what I can simply say is, like, let's say that if you're traversing in any directions, right? If there is any duplicate paths, like, and also if you're asked to find out a minimum path sum, it's a dynamic problem. Okay, we can cache it and reuse that operation. Okay, so now as we know that just by saving this value, it saved us one operation. How about saving everything, right? Like, I mean, will also we are not able, we can't save this one because that's the answer that we are looking for, right? We are starting from here, but at least we can solve the numbers that are later coming in, right? Like, I mean, wherever there is a duplicate path. So we'll start from here. So like, we'll update the same grid. We can actually copy and build a new grid, or we can update the same one. Okay, so let's say that what is the shortest path to reach to the end? Obviously, like, we are already on the end, so this will be only one, correct? For this one, what will be the minimum shortest path? 1 plus 1, this will be the 2, right? This will become 2. And for this one, 2 plus 1, like, I mean, currently we are on 2, and we'll be adding one more, so the answer will be 3. Correct. What we just did is, we'll be taking the right. Okay, let's say, let's take for this also, right? Here we have already computed for these two nodes. Now what we are going to do is, we'll do the same for this one also. So this time, previously what we had done was, we traversed from this and calculated it. Okay, instead of this, we don't have to traverse this time. You can also, like, just like these two guys did, right? Just like these two guys asked for the sum, you can also depend on this one. So this is already computed. So he will say that 2, he will say that 3. So 5 plus 3, 5 plus 2, which is minimum? First we'll find out which is minimum, right? 3 is 2, 2 is minimum, so this is the efficient way. So I will just erase this and got 7. So you can see, right, previously also we did a same calculation and we ended up getting the 7. Here also same. What we just did, we check these two numbers. I've got two options, I can go this way or I can go this way, correct? So if I go this way, there is already a calculation done. Say it says that if you take this way, you will need you will get a total sum as 2. If you take this way, you will get a total sum of 3. That's what it means, right? So which is efficient? I want a minimum, so I will be picking this one, 2. So 7, I will be, what the current number was 5, I will be picking this 2. Okay, actually we'll be solving in this order. So again, I will come to this one. So there is nothing I can get it from here, right? I simply can read it from this one, which is minimum. Obviously this is the only number that is left, so I can, 4 plus 3 will become 7. Okay, again we have already solved for these two. Now we will solve for this one. Okay, so now I can take either this path or this path, correct? So now let's read the values. Whatever the values, 7 is there, here is also 7, both are same. So minimum value is also same, so 7 plus 1, it will become 8 here. Okay, so now let's solve for this one. 1, what is like, will there is no way that we can go here, so we can simply read this value. I will it says that maximum this will cost is 2, so I will just update it this with 1 plus 2 is 3. So here again, I can go this way or this way, so which is minimum? This is minimum, right? So I will clear this out, 3, and whatever the number is here, 3 plus 3 will become 6, correct? And again we'll come here, finally we'll come here again, we'll have the two options here, one is this way, one is this way. Which is good here? 6 and 8. 6 is good, right? So we can take a minimum is this one, we'll take a sum of it, 6 plus 1 will become 7, right? So obviously out of this one we picked this direction, correct? And again out of this one we picked this direction, and here we picked it from bottom and we got it here. This is the highlighted answer in the, like, I mean, highlighted in the answer also, right? That's what we are trying to solve also, right? So this is the algorithm. I hope it is clear, like why, how we came to dynamic programming, and how did we decide like which values to cache and everything. Okay, so let's just summarize. Okay, so basically, let me just clear it out. Okay, so let's just revise. So we'll be started from here, and we need to go here. Okay, and we try to manually draw the patterns. Okay, like what are the paths that we can go. We could clearly visualize that there are duplicate operations that we are doing. Okay, so when there are duplicate operations that we are doing, we need to save it. Like, I mean, we need to reduce this number of operation. So by saving it somewhere. Okay, so saving this somewhere, it means that we are caching it. And whenever, like, I mean, whenever the term caching, or like, I mean, we are saving the operation and for the and reusing it later, is nothing but a dynamic programming approach. Okay, so now we got to know that we need to save it. And how are we going to save it? Basically, these values are dependent on the upcoming values, so we need to solve the upcoming values first. Okay, so that's why we decided that for this value, this is dependent on this one, this value, this is dependent on this one. So that's why we started from the right end, and we are traversing it to all the way till the top left. Okay, so every time we do it, so what we are going to do is, the only way that we can traverse is right or bottom, correct? So we'll check what is that right element says. So basically, we already know that for the last element, it's whatever the value that is presented, right? That is there. Like, I mean, we are already on that element, so it will be always one. Okay, so now again, for next element, will be depending on it. So whatever the element that it says, we will going to consider it and include in our path sum. Okay, that's how we built it. Now let's quickly check the code. So minimum pass sum, right? So initially we found get the measurements of the grid. So we'll be iterating from the top, like, what is it, right end to the top left. So we'll be coming from here. Okay, like, I mean, basically we are reversing, coming from the reverse. Okay, and here we need to make sure that we don't run out of the overflow. Like, I mean, we should handle it properly. Like, I mean, here, right, if you are in this direction, you should not go this way, right? If you are here, you should not go this way. You need to make sure that we are not going to overflow. That's what this condition is for. M minus 1, this is 1, this is 1. Okay, you will have to just visualize it so that it will be clear once, like, I mean, if you can see it, this is okay. And once we got it, like, let's say this the condition is for when we have a bottom and right element, right? We'll take a minimum, let's say. Okay, and this condition is for I think this is for bottom and this is for right. Okay, I plus 1, right? I plus 1 is, yeah, this is for bottom, and this is j plus 1 is, this is for the right side. Okay, so if we have only one element, we'll be doing this way. Okay, and yeah, like, I mean, we updated the same grid, we are not creating any duplicate grids, and we'll be updating it in place, and finally returning the whatever the minimum path that we are going to get it in the top, right? That's it. Yeah, thank you.